Hello students, welcome back. So today I will discuss electric field due to a finite rod, right? So let's start the session without any delay. So a rod of length AB is given here, right? The length of this AB, as you can see, is finite, and a charge is uniformly distributed across the length of this rod. That's why the term lambda has been defined here, because lambda is the linear charge density, right, which is lambda coulomb per meter here. And at a perpendicular distance of d from this rod, a point p is here, and at this point p, at this point p, you are supposed to be calculating the electric field due to this rod AB, right? So what is the process of it, right? So the basic formula which you have is that due to a point charge q, due to a point charge q, the electric field at a distance of r from it is E, which is kq by r square. Here we must note that q is the point charge, but here on the rod the charge is being uniformly distributed, which is not a point charge, right? So what I will do is I will consider a point charge at a y distance from here, right? And I will take a further distance of dy, which is very small. So the amount of charge which is confined in this very small length, which is dy, that very small charge which is confined in the length of dy, that can be termed as dq, and the value of dq will be simply lambda into dy, right? Here lambda is the charge per unit length, so in unit length lambda charge is there, so in dy length the amount of charge will be lambda into dq. Now this charge which is confined in this length dy, this can be considered as a point charge, right? So due to this point charge, you can use this formula to calculate the electric field at point P, right? So this dq charge, the value of electric field at P will be in the direction of, in this direction, and the value of d will be simply k times of dq upon, let us suppose the distance between this dq and the point P is r. So k dq by r square, right? Now put the value of dq, which will be lambda into dy upon r square, right? So the value of de here is k lambda into dy by r square, right? Now look at the value of de closely here. It is depending upon two variables, y and r. See, if you change the location of this point charge, let us suppose this point charge is here instead of here, both y and r will change, right? So what I will do next is I will convert both dy and r in terms of a single variable theta here, right? So from this right angle triangle, what I can write is that d is equal to r cos theta, right? D will be simply r cos theta. From here, r can be written as d upon cos theta, which will be equal to d into sec theta, right? So r can be written in terms of theta as d sec theta. Now, again using the same right angle triangle, I can write that tan theta is equal to y by d, and from here y is equal to d tan theta, right? Now differentiate this. This will give you dy is equal to d tan theta. Differentiation of tan theta will be sec square theta and d theta, right? So now put the value of dy and r here, right? Put the value of r and dy here in this equation of d. It will become k lambda times d sec square theta into d theta upon r square, which will be d square sec square theta. Now the sec square theta and sec square theta will term cancel out, and 1d will also be cancel out. So what I will get is k lambda by d into d theta, right? So the value of d now is been converted into a single variable, right? Now here d is a function of theta only, right? It is only depending upon single variable theta only, right? See, k is constant, lambda is constant, and d, the perpendicular distance of this point from this wire, will remain constant, which is d here. Now to calculate the net electric field, all I have to do is to integrate it. But as you can see, the direction of d will keep changing if I change this element dq, right? For this dq, the direction will be like this. Both magnitude and direction both will change. So you cannot directly integrate here. What I will have to do is I will have to take the component of it. So one component will be in this direction. Let's call this component perpendicular component of d, and one will be parallel to the wire wave AB. Let's call this component as parallel component, right? Parallel component, parallel component, right? See, the parallel component I'm taking in the downward directions because this length is bigger than this one. That's why the net will come out to be in downward directions. If this length would have been bigger than this one, then parallel component would be coming in upward directions, right? So it's very simple, right? It will depend upon the length, right? Now this perpendicular component of d will be simply d, and this angle is theta. So I can say that this angle is also theta. Both are opposite angle. So this angle will be a 90 minus theta, right? 90 minus theta, very simple. 90 minus theta, right? So this d perpendicular is equal to d into cos theta, and d into cos theta. Now put the value of d, which is k lambda by d into d theta. So it will become cos theta into d theta. So this is the d perpendicular component of d, right? Now I can integrate it because the direction is fixed. Direction is fixed. So upon integration, it will give you the perpendicular component because due to all the component, due to all the differential element, dq will be the perpendicular electric field will be in the same directions, so they can be easily added, and hence that means they can be easily integrated, right? Now coming to the so I will integrate it on the next page, right? So come to the next page. Coming to next page. So de perpendicular here is k lambda by d into cos theta into d theta. So net perpendicular component, to get net perpendicular component, all you have to do is to integrate this component, right? So integrations of this will give you the net perpendicular component, right? Now the question is, what will be the limit of this integration, right? So to understand the limit, let's come back to the figure. So here this is the figure, right? So integration is done basically while putting the limit. You will put the limit in such a way that it will cover the entire rod, right? Now I'm taking the value of theta from here, right? So now if I consider the clockwise sense as the positive sense, then automatically the anti-clockwise sense will become the negative one, right? So if I if I vary the value of from minus theta to plus theta, see, from here the angle will be negative. So this end is at minus of theta 2. So from minus theta 2 to plus theta 1 will cover the entire rod, right? So the limit of the integration will be simply minus of theta 2 plus of theta 1, right? So the integration of it, now the k lambda by d being constant, we will take it out of the integration sign, and the integration of cos theta. Integration of cos theta is what? See, the differentiation of sine theta is cos theta. See, the differentiation of sine theta is cos theta. So integration of cos theta will be simply sine theta, right? Sine theta. The limit is minus of theta 2 plus of theta 1. Now put the both the limit k lambda by d, it is sine theta 1, and minus of sine theta 2 will give you plus sine theta 2, right? So the perpendicular component of electric field is simply k lambda by d into sine theta 1 plus sine theta 2, right? So I'm saying this equation as 1. So this is the perpendicular component of electric field due to the finite rod. Now to calculate the parallel component, again we will do the integration under the proper limit. As you can see, the parallel component is dE cos 90 minus theta d sine theta, right? It will become dE sine theta, and again integration will be done from minus of theta 2 to plus of theta 1, right? Integration will be done from minus of theta 2 to plus of theta 1, right? So value of d is k lambda by d d theta, so it will be sine theta into d theta, and integration will be from minus of theta 2 plus of theta 1. Now take this constant, which is k lambda by d, outside of the integration sign, and the integration of sine theta will be simply how much? Minus of cos theta, minus of cos theta, and the lower limit is minus of theta 2 and upper limit is plus of theta 1. Now I can manage this minus sign by interchanging the limit. This is a property of definite integrations. I hope and I believe all of you have studied it, right? So this will be k lambda by d, and on managing this minus sign by interchanging the limit, it will become cos theta 2 minus cos theta 1, right? This will become upper limit and it will become lower limit, right? So on putting a value, you are getting the parallel component as k lambda by d into cos theta d minus cos theta 1. So the formula we're getting now is that perpendicular component is simply k lambda by d into sine theta 1 plus sine theta 2, right? And the parallel component of electric field is simply k lambda by d into cos theta 2 minus cos theta 1. So in the next session, I will discuss few problems based on this formula, because many times students remember this formula but they don't know how to use it, because the value of d and theta 1 and theta 2 has to be taken in the same fashion as we have taken in this derivations, right? So I will discuss a few problems in the next session. Okay then.